In this video, we want to talk about some very, very special right triangles. So you may remember these from geometry, I don't know, but one of them is going to be a 30, 60, 90 degree triangle that we have kind of illustrated right here. I'm going to get to that in just a moment. And the other is a 45, 45, 90 degree triangle. So these triangles are used quite often, even in the real world. Like I can look here in this room, I can see there's a certain angle here that's a 45 degree angle. Sometimes it's a 30 degree angle with the way the ceiling hits the wall. But you see this all the time in terms of construction and just very, very common occurrences with these guys. Now, this first one that we have right here is illustrating what happens when you have a 30 degree, 60 degree, 90 degree triangle. And the way that this is formed is think about an equilateral triangle. So that means all three sides are going to be exactly the same. All angle measures are going to be the same, so they're all going to be 60 degrees. But if I drop this altitude down here, and it becomes perpendicular with the base, then what you're doing is that you're splitting up this triangle, and you create this little smaller triangle, this half triangle on the other side. Now, just for the sake of discussion, we're making each of the side lengths be equal to 2n. N is just some number, it doesn't really matter. So it means this is 2n, this is 2n, and this bottom part is 2n. So when I cut that in half, you end up having, what you see here, that you still have the 2n for that long side, n for that shorter side, because it's half of the bottom, and the n square roots of 3. You may be wondering, where does that come from? Well, if you do the Pythagorean theorem and you solve for this third side right here, you'll find out that side is going to be n times the square root of 3. Now, to help us out here, so these are very set ratios that we have. 2n, or starting with n, double that to get the hypotenuse, and multiply it times the square root of 3 to get the middle side. If n is equal to 1, then it becomes this special triangle. So you have a base of 1. Your hypotenuse is going to be double that, because you can kind of imagine that you have, here's this half triangle. I just kind of double that to form the equilateral triangle. And then you have this middle side right here, where you have the square root of 3. So we replaced n with 1, and this is what we get. Now that we have this triangle set up, where n is equal to 1, let's look at the ratios of the side lengths so that we can come up with values for our trigonometric functions. And let's start with 30 degrees. So I'm just going to put that here as a bit of a heading. And let's see, what is sine of 30 degrees? Sine is supposed to be opposite the 30 degrees over hypotenuse. So it's going to be opposite of 30 is 1 over the hypotenuse, which is 2. So the sine of 30 is 1/2. Well, what about the cosine of 30 degrees? Well, that's going to be the adjacent side to 30 degrees, which is going to be the square root of 3 over the hypotenuse, 2. The tangent of 30 degrees is going to be opposite, 1 over the not hypotenuse, the adjacent side, silly me, which is the square root of 3. And if we rationalize this, we end up with the square root of 3 over 3. And we might as well go ahead and fill out the rest of these. So if I need to find the cosecant of 30, that's going to be the reciprocal of the sine. So that's just going to be 2, which makes sense because remember we talked about the range for cosecant and secant being from negative infinity to negative 1 and 1 to infinity. So their absolute value will be greater than or equal to 1. The secant of 30 degrees is going to be the reciprocal of cosine, so that's 2 over the square root of 3, and when we rationalize, we get 2 square roots of 3 over 3. And the cotangent of 30 degrees will be the reciprocal. So here's this guy right here. If I just flip that over, I get the square root of 3, and I don't have to rationalize. But now let's check out what happens with 60 degrees. And let's connect this back with discussion that we had earlier this section about co-function identities, right? So if I want to find the sine of 60 degrees, that should equal the same as the cosine of 30 degrees, right? The cosine of its complement, which is going to be, you see here, the square root of 3 over 2. Now, if you actually were doing the sine of 60 from this diagram, you would have the opposite, square root of 3, over the hypotenuse, 2. So it does work out. If I want to do the cosine of 60 degrees, I just need to look at the sine of 30 degrees. So that's going to be 1/2. And if I want to do the tangent of 60 degrees, that should equal the cotangent of 30 degrees, so the square root of 3. Again, you could also see this as, okay, tangent is the opposite over the adjacent, so square root of 3 over 1, the square root of 3. The cosecant of 60 degrees should equal the secant of 30 degrees. And that's already done for us, 2 square roots of 3 over 3. The secant of 60 should be equal to the cosecant of its complement, so the cosecant of 30 is 2. And notice how this does line up with expectations. Cosine of 60 is 1/2. Secant, which is his reciprocal, is 2. Yeah, that makes sense. And then finally we have the cotangent of 60, which should equal the tangent of its complement, which is right here. So the square root of 3 over 3. All right, so that's one of our special triangles. There is another special triangle that we want to look at, and that one is going to be related to 45, 45, 90-degree triangles. And we're going to look at that in just a moment. Then we're going to put everything together.